So, as I said that real gas is more complicated because it is it's like an infinite series, right. We need several possible coefficients in order to express the profile the variations of the compressibility with pressure or volume. A simpler interacting system was proposed by van der Waals in 1873, actually before the real gas virial expression came. It was proposed by van der Waals to understand that how an interacting gas molecules would look like. So, what will be the equation of state for a simpler interacting system, not as complicated as real gas, neither as simple as an ideal gas, somewhat in between, a compromise. So, the compromise is done this way, that the first assumption is that we have PV equal to RT, right. This is with the condition that there is no interaction between the particles, and therefore two particles can even overlap on top of each other. However, let us say we say that the particles cannot overlap on top of each other. So, they can be as close as touching each other. So, in that case one has to consider the volume B of the particles. Now, then overall volume of the system will become V2 V minus B. So, this is a molar volume, this is molar volume of the particles alone, and this is molar volume of the system. So, then our equation goes to P V minus B equal to RT. Now, we rearrange this, we rearrange by P equal to RT by V minus B. So, this is one part of the correction from ideal gas, that we use a finite size of the particles, finite volume of the particles. So, imagine all the particles are touching each other, we will be able to calculate the overall volume, and that will be the volume of B. Actually, it is not quite, let us say volume of one particle is x, then there are n number of particles, it will be xn, that xn is equal to B. But even they touch each other, there will be interstitial spaces and all that. So, therefore, it is not equal, that is why I said it is not equal. So, anyway, once we have the volume, we can rewrite that. Now, second correction would be that if there is interaction among the particles. So, this is assuming no interaction, right. It is only assuming that they are like hard sphere, like two marbles, they cannot be on top of each other. Even if you bring them, it will be as close as touching each other, right. That is called hard sphere. But let us say you say that no, they also have interaction, it is not just their size, they are also interacting with each other, which means they are having an attractive interaction. So, in that case what is going to happen is that, imagine a box of full of molecules. Now, how does this molecule put pressure on the wall? It put pressure because it goes to and hits the wall, it gives force on the wall, and force by area is the pressure. Now, if there is interaction between the particles, then this particle which is on the close to the wall will be pulled inside by the other particles. A particle which is inside, there is force pulling it from all sides. However, the particles which are on the surface, there is some asymmetric force coming out from the inner molecules, which is pulling them towards it in an attractive manner. What will happen in that case? Will the pressure be more or less on the wall? Less. So, that less pressure is formulated as A by V square. So, why it is V square? Because on one particle there is a all other particles are which is attracting it towards it. So, therefore, it goes as 1 by V square. So, now we have this particular equation of state, which is called van der Waals gas equation of state. Why it is so good? Because it gives you a feel of real gas, but much less complicated way. and it is tractable. You know that B is the size and you know A is the attractive interaction. So, given A and B, we will be able to actually understand or change the behavior of this particle. Now, how do we calculate now the compressibility factor? So, this is the equation of state. Now, let us say we try to write the compressibility factor. So, I can actually do that again, that is a simple derivation. PV equal to RT. Now, PV minus B is equal to RT, and then we get P equal to RT by V minus B minus A by V square. So, this is our van der Waals equation of state, okay, because we do not have to remember that, we can always start from ideal gas and come to that. So, P equal to RT by V minus B minus A by V square. So, that is the van der Waals equation of state, right. So, now we have to calculate Z, which is PV by RT. So, therefore, in the case of this particular equation, equation number 1 I can multiply by V and I can divide by RT. So, multiplying by V and dividing by RT, what I am going to get is V bar by V minus B minus multiplying by V and dividing by RT. I am going to get this. So, this is now the compressibility factor. We will simplify it, divide by V in the numerator and denominator here. So, 1 by 1 minus B by V bar minus A, 1 will cancel, by VRT. So, now we will have to use one trick, is that we know that 1 by 1 minus x can be written as 1 plus x square and things like that, right. So, we are going to use that series. How our x here is B by V. So, let us write that 1 plus x, which is B by V, plus B by V square plus dot 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 minus A by VRT, which is 1 plus, now I have the V common. So, B minus A by RT multiplied by 1 by V plus B by V square and higher order. So, now we have written the compressibility factor in terms of the series that we were writing for real gases, right. So, now do you identify the B here? So, this is our B, I cannot write here. So, our B here is B minus A by RT, okay. So, what does it mean? So, it gives us a lot of information. First of all, we can always neglect anything higher order, second order or higher. We can always truncate it at the first order, which is 1 plus B minus A by RT into V. Now, you can see here is that, so we have already taken minus of A. So, a negative value of B indicates basically positive value of A, that is how that. So, whenever the term A by RT is larger than B, we are going to get a negative B and we are going to see a dip, right. So, let us say at what will happen at low temperature. At a low temperature, this A by RT quantity is going to dominate, because temperature is in the denominator. So, at a lower value A by RT will be higher, and therefore, this term B minus A by RT will dominate, and therefore, it will become negative. Therefore, you see that at a lower temperature it was going down, but at a higher temperature A by RT can be neglected and you simply have 1 plus B by V, and B being positive quantity because it is a volume, it is going to always be positive, larger than 1, and that is what we saw in the real gases, right. So, B minus A by RT. So, let us see if I have that. So, this derivation is exactly here, which we have just now done. So, second B real coefficient B is given here, which I have done. A is therefore relatively more important at low temperature and B is relatively important at high temperature, because at high temperature A by RT term is going to be neglected. So, therefore, B is more important at that value. And here, so now the thing is that van der Waals gas is not a real gas. However, we can use this van der Waals equation to fit at least smaller regions of the volume variation, and thus we can arrive at certain values of A and B, and you can see those values are here. And we can also calculate the Boyle's temperature, where B minus A by RT is 0. So, simply B equal to A by RT, and therefore, T B, which is Boyle's temperature, is A by RB. Okay. We want to show you how with the two parameters A and B the equation of state changes. So, for that we are using some software called Mathematica, in which one can plot both 2-dimensional and 3-dimensional pictures, profiles, and with that we can show you how, as a function of A and B, the quantity changes. So, just to give you a brief intro to Mathematica. Are you familiar with Mathematica software? Okay. So, remember that we do there are different softwares like programming softwares, where you can write programs for numerical problems, right. You can do differentiation, integrations, and get numbers. Mathematica is one such software where you can do analytical calculations, which means that you can do differentiation, integrations, and lot more difficult mathematical tasks using this particular software. It is so good that even mathematicians use it regularly. You can plot 2-dimensional and 3-dimensional figures in this, and is extremely useful. Not only that, it is also there are a lot of demonstrations available to understand a particular concept. Let us say you have a complicated function and you want to see how it behaves. You can plot that in Mathematica and see that. So, you saw that our equation, van der Waals gas equation, was slightly complicated, right. So, one can plot and see how it behaves as a function of both those two parameters A and B. So, if I remind you, the equation was P equal to RT by V minus B minus A by V square. So, that is the van der Waals equation of state, right. So, now if I have to plot this quantity, so we have to express the quantity Z, which is PV by RT, right. So, we have to so this Z is compressibility factor PV by RT, right. So, that means if I now multiply PV by RT on both sides of this equation 1, I am going to get V by V minus B minus, I am multiplying with V and dividing by RT. So, this cancels and I get V. So, Z becomes V by V minus B minus A by V RT. Do you see this quantity V by V minus B minus A by V RT? So, what they do is that they just plot the value of Z and vary V basically. You can plot the whole right hand side quantity. You do not have to really separate it out, right. So, you can plot, you can put value of V as 1 and 2 and things like that, and just calculate the corresponding Z value. Okay. So, when you do that, you get this expression which is shown in red color. Okay. So, what you see here is that for helium gas, you see that the Z value, even for very low volume, it is above 1, because A is small and B is also small. Now, when you go to hydrogen, so when it is helium, A is 0.03, when you go to hydrogen it is 0.24, that means it significantly increases, right, almost 8 times. When you go to nitrogen, it is 1.39 A value, is much more, and you see it has already come below 1. Now, you go to carbon monoxide, it is below 1, oxygen it is even below, carbon dioxide and ammonia, you see how it is, and then finally water, which has the highest value of A. And remember we told you that A indicates interaction, higher the value of A, stronger the interaction is between the particles. So therefore, if A increases, then automatically the compressibility will be lower than 1. So as you see that because of the A, it is going lower than 1, and we have seen that when it will be larger, then it will go above. And B also has B will not vary so much, because B is just the size of the molecule. So going from helium to water is not that significant. So for example, it is going almost 30-40 times between helium and the water, but B value is not changing that much. It will be at most the double, right. So B value of water is 0.03 liter per mole, and for helium it is 0.02. So you see B value does not change that much, only the A value, which is interaction, that changes strongly, and therefore it has that kind of effect.